Hello everybody and welcome to Handmade Hero, show where we code a complete game live on stream. So a couple things we want to do today. We'll see what we have time to get to. But if you remember where we left off last weekend, we had done, I think we can give ourselves a little pat on the back for doing a bunch of good debugging on the lighting system, and I think we're now ready to start pushing it forwards a little bit. And starting to do some more interesting stuff. Our goal is to just get the lighting to a point where we're happy enough with the performance and happy enough with the look to move on. And one of the things, if I zoom out right now, you can see is I'm really happy with how this is converging. There's a couple things about it that I think we need to improve in terms of the back-end side of things. Certainly the sampling, we want to blur across the voxels a little bit better so we have less squarey interpolation on the lighting. I think that's a performance concern, meaning we'll have to do some work to make sure that doesn't tank the performance, but it's not really too worrisome. Like, it's not like I'm like, what would that look like, right? So I think that'll be pretty easy for us to deal with. And then the other thing is, in terms of reducing the sampling noise, maybe getting some less flicker in there. Those are really the two quality issues. There's not a lot more, honestly, on the quality side of things. It's looking surprisingly good for completely dynamic lighting, no pre-computation whatsoever here. And that's pretty unusual, actually. So I'm pretty happy with how that's turning out. And so I think we want to do those, certainly, but what I'd like to do first is refocus on performance a little bit now that we've gotten the bugs worked out. I want to flip back over to our standalone performance tool and really turn the screw a little bit on the cube tracer, because now that I'm pretty confident that it's what I want, there's a couple things I want to do to try to get its performance significantly higher. And that'll let us do two things. One, it'll let us target 60 frames a second on high-end machines, even with lighting in software completely, no GPU assist. And the other thing that I think it will do for us is, if we would like to, we can also do another thing, which is targeting 30 frames a second with much higher quality lighting. Because we could double the number of rays per frame if we wanted to, right? So we have a lot of options there, but regardless of what we choose to do with it, there's never, you never don't just want faster performance from the raycaster, right? So what I'd like to do here is just start taking a look at that. So let's take a look at the stuff we have set up for that. And what I'm going to be using mostly for this is our HH Light Prof that we've made. And so what I really want to do today is, now that we've done a bunch of work on the lighting system to kind of extract out we can switch between the A, B, and the regular. I'd like to do a fresh capture of a particular lighting environment into HH Light Prof, and then I'd like to run the profiler on it. And that'll require a little bit of work because we changed how we're storing things, so we just need to change how we're dumping them as well. So if you take a look at the update lighting call, what I want to do, let's see here. So what I want to do is, if you take a look at the update lighting call, you can kind of see how we come through here, and we do a bunch of work to, do the build diffuse lighting maps and all this sort of stuff and all that, lining up the voxels. We do all this stuff, and then we call internal lighting core. And internal lighting core is the thing that does all of the work. And so what I'd like to do here is, I'd like to take internal lighting core, and I'd like to make that be runnable again outside in HH Light Prof. So here's internal lighting core here. And what you can see is we pass all the same stuff to it here, right? You can see here we've got basically the same thing. But we don't have the occluder and occluder count thing. Like, if we started building HH Light Prof, we get errors there. And furthermore, we would need to load different stuff. So if you look here, we load these pieces of information. Those pieces of information are not sufficient. What we actually need to load now, if you look at all of these here, we We do want basically all this stuff. The only difference is the result light boxes and result box refs, those are gone because we don't have such a thing as those results. And then in here with the source lighting dump and the source light boxes dump, I think all we need at that point is just the occluders, right? So I think the occluders are all we would need there. Now we can also choose to dump the other table information, but I'm not sure that there's any real reason to. So if we look at the other pieces of information that are stored in tabular form inside the lighting system, because here's the lighting system here, what you can see is that there's a walk table, there's a weight map, and there's sampling spheres. The weight map will be stored automatically because the weight map is just, if we write this out, the things that won't get stored are like these pointers, right? And if we look down here, you can see that we've got, just a few other pointers here, but they are going to get built as part of it, right? And you can see here I'm even saying that they're allocated in the temp arena. So we don't have to preserve these because they will get rebuilt by the internal lighting core. We don't have to use the debug lines because we're not going to be storing the debug lines anyway. And so if you take a look up here at what we're doing, really all we have to do is rebuild the light sampling walk table and the sampling spheres. And as far as I know, there's no reason why we can't just do that, right? Okay. So I think we should be able to just proceed directly. And what I want to do here is I want to go to the internal lighting core code. And what I'm going to do is I'm going to, right before here where we do the debug dump, I'm going to delete the part where we were doing the result dumps because we don't care about that. These results we do want because this is what we're going to compare against. And these we do want, but we want to modify it slightly. So in here where we do the lighting dump, that should just work because it's still the same thing. It's just a different struct now. And then in here, what we want to do is have a new thing called like source occluders or something, right? And all that's going to do is in here, you can see we have an input box count and an input boxes. So I'm just going to say like, look, input box count. And I could just call this boxes because why not? An input box count, which is going to be the size of whatever this input boxes thing is. And then it's going to be a pointer to the input boxes, right? So that'll dump, this series of dumps will dump everything, I think, that we need. And then what I'm going to do is I'm just going to pop over to HHLightProf, and I'm going to say, okay, now if this is called, and I guess we can leave it the same name even, light boxes. So now if we just continue loading this up, right? I don't really know what this is for. We'll have to see. I guess it's because we don't know ahead of time. Yeah, what is that about? Oh, I see. So this was just telling it to give it some extra space because we might need to use, we might push off of the end of that array. I don't know if that still happens. In fact, I'm pretty sure it doesn't. So I think we can just get rid of that. I'm going to go ahead and pull that out. And just, we'll leave it in here because there's no reason not to leave that feature in if, it's not hurting us to have it in there. It's just an addition that happens here. But otherwise, I'm going to get rid of it. And so if we look at recompiling the lighting code here, you can see that that compiles cleanly. And we're not compiling HHLightProf right now, so I got to jump back in there and add that. So if I go back to HHLightProf, I guess I was already in it, sorry. What I want to do is take that build, and you can see here that like I've remmed out some things. And so one of the things I remmed out here was HHLightProf. So I'm going to go ahead and rebuild it. And what you can see here is there's a bunch of compile errors. Those are the differences in the old way we had the lighting set up and the new way we had the lighting set up. So we just have to go through and basically excise the parts. We made things a lot simpler and better. We cleaned up the lighting code quite a bit because, it was kind of old and crufty, and now we've got it sort of minimized. It's still a little cruftier than I would like, and that's because we're still able to run both systems in place. We can run an AAB caster and we can run the grid caster. I'm pretty sure I want to stick with the grid caster, but until I actually do some performance analysis and improvements here, I'm not quite ready to say yet. So we're still a little cruftier than we will be in the end, but we're a lot cleaner now. So a lot of this stuff we were doing when we were just sort of hacking on it to try and explore, we can now get rid of. So we don't have to do any more of those transforms, and we don't have to worry about a lot of these like solution box count, any of this stuff. None of this stuff matters here. I think we can just go ahead with it. The light boxes, when we load them, the size of that system is what's going to tell us how many boxes there are. So what we need to do here is we need to say, okay, the input box count, so like the occluder count, what we were calling before, that's actually going to be the source light boxes divided by the size of one of these lighting boxes, right? So we need to just get that out because we're going to have to pass that to the internal lighting core when we go to run the internal lighting core. So like in here, right, if you take a look at the parameters this thing has to pass, you can see that we've got some of them. We've got the spec atlas, the diffuse atlas, the lighting queue. We're nerfing because we're not trying to run multi-threaded. We've got the input box count, which needs to go here. So that's the occluder count. And then we've got the input boxes here. I don't remember source light boxes. I'm not going to remember what that's called. And then we got the repeat count. And the source light boxes, I think I don't really remember what a buffer looks like, but I think it's just a size, right? Oops. There we go. So you can see it's just a count and a data, right? So I should be able to just pass the data here, like so. And maybe I won't call it, maybe I'll call it source light box count. That's just going to be the count divided by the size there. So we'll just go ahead and say source light box count. And that will give me a correct pass through for that data, right? So hopefully this can be called now. It looks like this is unhappy about that though. Oh, because this is U32 and we don't actually know that it has to be, but trust me, I'm not going to be writing out that many. We're not going to overflow a 32-bit integer with the number of boxes. Heaven help us, that would not run at 60 frames a second. So I think that's all good. The total input boxes is getting printed out here. There's no reason not to continue doing that. I mean, we have it. I don't know that we care about that information particularly much, but there it is. Okay, and so now in here we have an issue with the lighting box. This has not been casted, so let's just cast it here because it's just a blind buffer we loaded off disk. It doesn't know what the type is. U32 to U16, so I guess this number here has to be a safe truncate to U16. It can't be a large number because the system doesn't support it. If we look at result light boxes in here, you can see us just like checking to see if the results of the light box modifications worked out. Like I said, we're not doing that anymore. So that can just kind of get removed. And if we look down in here, same thing, right? This is not, none of this stuff is relevant anymore. So once we're done with that, I think we're pretty good to go with the exception of there's some setup work here that's not really appropriate. So if you look at here where we load in the solution, for example, one of the things that you'll notice that we're not doing is we're not building those tables. And if you take a look at what's going on in the actual lighting code itself, so in update lighting, you can see that it does some table builds. So it does a compute walk table and a build diffuse light maps. Build diffuse light maps is fine because like I said, that one's like welded directly in. The compute walk table call, not so much. Compute walk table is a blind pointer. It's not going to get written out. We could write it out, but there's really not much reason to do that when we could just say, look, we loaded all the dependent data, so just rebuild it here. We know that we can, and it just doesn't seem like there's any reason not to. So what I'd like to do there is just say, all right, we know that we need an arena anyway, and so let's just build it. So I'm going to go ahead and say after we initialize the arena, which happens right here, I'm going to go ahead and build the sampling walk table here. We're going to pass the temp arena. And all of this stuff, I think, should remain the same, because all of this stuff has all been written out, and off we go. So we need to do that. And the other thing we need to do is we need to initialize the sample direction table. But I think because we switched to doing that as a direct lookup rather than looking it up from inside the lighting solution, I don't think we actually have to do anything there, because it's just a global. It was just an include that's just the hard-coded table that we welded in. So I think that would get us everything. We'll find out pretty quickly, because if I forgot something, we will immediately die a horrible death when we try to run it. But let's go ahead forward with it. So what I'd like to do here is just get us to a place where we can do the write out. So if you take a look at internal lighting core, so I'm gonna go ahead and run here, and I'm gonna set a breakpoint at internal lighting core. And if we take a look at that code, so I don't actually know why it's not, there we go. So if we take a look at internal lighting core here, you can see that we've got this light box dump trigger. And if the light box dump trigger global variable is set to true, it will dump the source lighting out. And so what I should be able to do here is I should be able to set this to true. I don't know. I guess I don't really remember. I don't think Remedy can edit values though. I think that's something that George hasn't added yet. So I remember we didn't quite do it this way for that reason. Normally what I would do is I just edit the variable here. But I don't think Remedy supports that yet. It might. I mean, I might just not know how to do it properly, but I don't think it does. So I'm pretty sure the way we did this is we just set the value to true once, and then we let it clear it to false here using the dynamic reload. The problem with that, if I remember properly, is I think we'll have to fix the dynamic reload first, because I think dynamic reload is kind of busted, right? Something about the table offset was like not correct. And to be honest with you, I'm not sure what it is. So we should investigate that anyway. So let's just fix that bug first. So you can see the lighting's working just fine in here, and here's like a debug draw of the table walk, right? Let me just go ahead and do a dynamic reload. I'm literally not going to do anything. I'm just going to recompile, right? So it's just going to reload the same exact code, and I just want to see, like, do you see how it broke, right? It's like now there are no steppings, right? It's like the table just went away. And so I don't know what is going on there. Like, I have no idea why that's happening. And so we should take a look. So it's like it won't be re-entering this piece of code, but I'm not sure why that would matter. Do you know what I'm saying? Like, this piece of code, it sets a bunch of memory to point to stuff, but it should just work, and I don't know why it doesn't, right? We probably could patch over it by going in here and on reloads, forcing it to redo this code path. But the fact that we have to do it seems odd to me, and so I'd like to know why before I do that. Like, rather than just patch over it, I want to know what's going on, because I don't see what would be going on there. This shouldn't be getting reset unless we reset it. So what changed, right? And we are we are using this sample direction table, right? Which is this sort of like hard-coded table that we're accessing off. That's all well and good, but we don't weld anything into it, I don't think. Like, we don't weld pointers into it anywhere, unless I'm just misremembering. So they're just offsets. And if they're just offsets, then I would think that this would just run fine. And plus, the table should be the same in both versions of the DLL anyway. So I really just fundamentally don't understand what's broken. So what I'd like to do is go ahead through here and see if I can, if just by stepping through the code perhaps, I can see like what's going on and why we're getting such a weird result. Okay. So I'm going to switch this to a debug build real quick. And I'm going to verify that the problem still occurs. I mean, it's always possible that you have a bug that only happens in release mode. We don't really have very many of those, hardly ever on Handmade Hero. So it's probably not, but rather than, hunting for something that I don't know exists, I'm going to first verify that if I do a rebuild here, the lighting will shut down. And it does, right? You can see that as it finishes blending out the lighting, now we're not taking any steppings, right? And it seems fairly clear that the problem there is one of the walk table not working. And so I want to take a look at what's going on with the walk table. Now, just to refamiliarize myself with that, you can see that here's the walk table entry. It's just like a T terminate and a D grid value. That's all that's in there. And if you take a look at the walk table itself, you can see that there's just there's a pointer to just a giant set of memory there, right? And if you look at what happens during compute walk table, it takes the solution table memory, which is just a thing, like any other piece of memory. And so again, I'm not sure why it would be having any trouble. Looking through this routine just to make sure there's nothing weird going on, you can see it just does a standard push of that memory that's remembered by the table. And it just does a straightforward build and writes the data in, right? So again, I don't see a lot of explanation here or a lot of like clues as to what would be going on. So what I want to do is I'm going to first, because I happen to be in the broken mode right now, I want to go ahead first and just inspect these values to see what the heck is happening. So I should be able to pop a breakpoint in here in the internal lighting core and just quickly use the debugger to look and see what I'm getting in all of my data here. You can see like things in the diffuse map and stuff like that here, and I can just spot verify that they make some sense, and they do. I wasn't assuming anything would be weird about that sort of stuff anyway. We have pretty much what we would expect for all this stuff. I'm going to concentrate on exactly what I said, on just taking a look at the walk table, because that's the thing that I don't really, I'm not confident that it's remaining correct, because the bugs I'm seeing seem to be related to that. So this is the light sampling walk table, and I just want to look and see what's in there, right? So I'm going to go ahead and say light sampling walk table, and I'm just going to look at some entries, right? Oops. So here's what the light sampling walk table looks like, and if we kind of just go through it, there's nothing particularly odd about it. It looks like kind of what you'd expect, right? Those are just stepping in certain directions. So, I don't really see much in the way of a problem, right? That just looks like what I would think it would look like. So I don't think there's really much that I can tell about that. Like, I can't really see what the issue would be. So I'm going to have to look a little closer and just find out like what's happening with the stepping. We may have to turn off multi-threading for this because I don't really have a good way of making sure that, like, I don't have a way to single step just one thread. So I kind of need to figure out what's up with that. If I go take a look at where the step encode's actually happening before I turn it off, before I turn off multi-threading, I should still be able to see pretty easily what is coming out of the grid raycast. So if I take a look here at the grid raycast, which is right here, I should be able to see like what walk table things I'm pulling out here. So if I just go ahead and run, I should be able to see what's going on with the walk table when I grab one of these out, right? So there's the walk table there. You can see that the values are nothing particularly fancy, right? And if I take a look at the sample directions, I guess, so, this is interesting. So this could be an explanation for where we're getting the error. So this pointer, when we load up the sample directions, this is going to be different between the two runs because it's static data that's in the executable. I don't have any reason to suspect that, like, I don't know why that would fail, because when you load the new one, it should just use the new table, but the new table is the same as the old table, right? So I don't know. Oh, yes, I do. Wow, that's subtle. I like it. Here's the problem. And we probably should fix this. So the problem is that if you take a look at what happens is when you do the build, so in there where we do the walk table build, if you take a look at the way we chose to do that, which was kind of not really a choice, it was just a quick thing we hacked in there, this gets filled out by the build. So we're actually writing into the static data table. When we then reload the new static data table, it's wrong. See what I'm saying? So I think probably what we'd rather do is block copy this data, right? I think what we'd rather do is just block copy this data. Now, I think we may end up eliminating this anyway. So I'm not going to spend a lot of time worrying about this, to be completely honest with you. So, there's that. But I think what I'd like to do here is say, all right, this sample direction table that we were using here, I think that's all we really need. I'm just going to go ahead and nerf it for a second. And so what I'm going to do is I'm going to see all the places that use it. And I'm just going to change those to accessing a local copy. Right? That's all I'm doing there. Okay. And so I'm just going to copy this table up is what I'm going to do for the immediate moment. And it's a bad solution to this problem because we shouldn't really have the problem to begin with, but I think it's good enough for now. So inside compute walk table here, what you can see is every time we go through here, you can see us right into the direction here. And so what I want to do here is change the way this is working. What I want to do is I want to take the light sample direction, the light sample direction, and I want to set both of these. So I'm going to do a copy of these two, right? And what I want to do here is I want to just pull just this out. So this will come out of the table. And then the actual thing that we write will not, right? That way, this is just a copy that we keep for ourselves internally. So then in here, when we do sample directions, this is just going to be a push array in the memory for the array count of the sample directions table. And that just gives us, what was it called? Sorry, light sample direction. That just gives us a copy. Again, not a fantastic solution and probably not what we'll go with eventually, but it's good enough for the moment. Okay. What is it called? What's the problem? Sample direction table. Sample direction table. Oh. There we go. Okay. Sample direction table. Sample direction table. And in this particular case, I guess we kind of need the solution. What we could do here is just have this be done outside as well. So where we're doing the compute walk table here, I can just do that and know that that'll get lofted later. So that's actually fine. So this... Interesting. So I think we would want this to actually look like a source and a dest at that point. Maybe. All right. And again, that's just so I can have some way of copying these things back up. This looks, what's the problem here? Undeclared identifier. I agree with you. I thought we had sample direction table. Oh, yes. We'll unnerf that now. That all seems fine. This needs a source though, so I guess we need to do 2 of these. Like so. Again, this is ugly because I just don't care at the moment. I want to do this a little bit differently, and I just don't want to do it right at the immediate moment. Okay, so compute walk table here needs to do the same thing. So exactly what we did before. This code has to occur in the test routine, same way. Otherwise, we're good. Okay. So let's see if I can get that to work properly now. And we'll just take a look at what happens through here. Run, please. Okay, so if I now go back and recompile and force a reload, just want to make sure everything's kosher. Looks good. So let's go back to our release build. Here we go. So here's the release build, and I should now be able to go somewhere, like say right here, and I should be able to do a rebuild, and the lighting should remain correct. And it does. And so all I'm going to do here now is literally just take the dump, the lighting debug dump, and whatever that thing was called, I don't remember. lightbox dump trigger, I'm just going to do a build with that set to true to dump this exact data, right? So during the reload now, it should dump the data, and now I can just put it back to false. And in theory now, inside the Handmade debug directory, we should have a bunch of dump files. So here you can see the two atlases, both their starting and ending values. You can see the boxes that were input, and you can see the base lighting setup. So one of the things that's stupid about this, you can see here, is like that size is really large. And I'll be honest, I think it's just the diffuse weight map. So I guess it's fine. But it's literally just this huge piece of data. And you can kind of see why this sucks. This is why this diffuse weight map is bad too, right? It's one of the reasons the diffuse blur probably sucks, is because you can see that like the diffuse weight map is this huge 1 megabyte thing, right? We'll be talking about that a little bit later as we go to do optimization on the non-raycasting part of the lighting system. But it's just worth noting that it's, it's not good. So let's go ahead and try to get our HH Light Prof system working. And this is just going to be trying to debug any part of this that had to do with the new way that we're dumping things. And we just have to go make sure that that actually works at all, right? So if we run this, we should be able to start debugging anything that doesn't work properly. We're having some, oh, yes, right. That has to be those aren't arenas at the moment. So we have to make sure that when we're doing the HH Light Prof, we always use the little dummy arena we set up to push things on. Let's just make sure that's right. One more time. Okay. So debug lines we don't have set up here. So what we'd like to do here is make sure that debug lines are nerfed. So inside update debug lines, probably want to force that to false. So no matter what happens, once we load it, we just want to say, look, don't draw that, right? We really, really don't want you to do that. Because we don't support debug lines in the external, there's nothing to draw, right? So if you take a look at what's happening now, you can see that at least we are running it. The total error is pretty low. It's hard to say to what extent it is or isn't right. Again, because floating point will change between these two builds. Hard to say. This is the debug build as well, so it's going to be even more different. We'll run the release build in a second, and then we can get perhaps more of a sense of it. But yeah. So let me go ahead and actually run. There we go. Oops. So one problem with that is it exits before I can see the results. So let's just run it outside. So this is HH Light Prof and it's run in Handmade Debug, so I can do the exact same run here. And again, I'm just curious what the results are that we get, right? So I think we're in good shape here because that 7.64 is actually a really, really, really good number. Because I think I can improve the speed of the Gridcaster like dramatically from where it is right now with not too much work. And that's already like the same number that we were getting out of the AAB tester roughly. So let's just see. I mean, it could be way worse because we could have not picked quite the same location. So, you know, apples and oranges. So I'm just going to switch this to the use lighting grid off case to run the AAB tester. So the AAB tester may still beat us here, right? And we'll see. Obviously, the error per pixel will be totally different because the AAB caster is different. But yeah. So what you can see here is actually the difference between these two is not particularly high. And that's exactly what I was hoping for, because I think the grid caster is currently quite slow compared to what it could be. Now, one of the problems that we have here is, you know, we are not accounting for how much time the diffuse blur is taking. So if like we literally didn't cast anything, we don't really have a baseline for that either. So I might just quickly say, look, let's do a quick, we'll open up speed crunch here, and I'm just going to copy these numbers in, right? Oh, you know what? Let me use a notepad or something. So if I just really quickly, or you know what? Maybe I'll just put them up here. Who cares? It's my source code. So I'm going to say here that like, so the grid caster started at 6 point, well, you know what? And the AAB tester was there. And what I want to do is do a run where I don't cast at all. So we'll switch back here, and in grid raycast, like, if we assume that like literally we just don't do anything, so it's like, hey, what we're gonna do is that. Like, that's the work we're gonna do, right? Oh my God. Are you happy now, compiler, you piece of crap? So if we're not debugging, by the way, if I may for a second, because it seems like compiler, like language spec authors and compiler vendors seem to be completely divorced from any notion of how people actually make code at all, right? In any sane world whatsoever, there would be no such thing as a compiler error or a compiler warning. There would be two separate things called, I could not compile this. Like, I literally could not figure out a way to produce code because I don't understand what the input is. And you can call that an error if you want, call it whatever you want. It's a compiler didn't produce the executable. That's one thing, okay? And if that happens, you don't produce the executable. Then there should be another thing called things I noticed about the code, and those should go to a separate frickin' file. And if I want to see them, I'll load it up, right? I always want it produced, and I always want to see them, but I want them separate. So what ends up happening is you have to treat warnings as errors, because otherwise you just have all these error warnings streaming through, and you can't find your actual errors, and you don't know which errors are wrong or right? It should output them to a file, and then just let me mark the ones that I am okay with. And then those just don't get, just put, like I just copy it from the file into a separate file that's like, ignore these specific warnings. Because it's not like the type of warning is the thing I want to ignore. It's that like, yes, I know that code was unreachable. It's supposed to frickin' be unreachable. That's what the return value is for. Let me tell you that. But of course I can't. Another way you could do it is just say like give me a keyword that I can just stick in here that's like, I know it's unreachable. It's supposed to frickin' be unreachable, right? Absolutely frickin' wasting my time all the time. Like, figure something out. Instead of spending like all your time on ridiculous, stupid crap that no one cares about and that never works, like your next weirdest template nightmare, try making a feature that actually a programmer can use to make their program more convenient to write or debug. Like, just try, you know, spend 1 day on that instead of how are we going to, you know, make this ridiculous RAII thing with 27 levels of exception handling and 34 different templates to try and figure out that the thing needs to be allocated from a pool. It's just like unbelievable. Okay, so I now want to try and run with no cast. So what's going to happen is every time it tries to cast, it will just immediately fail out, and so we'll get the measure of the timing with none of these things, right? And the only reason that I wanted to do that was because I need a baseline value to know, like, you know, it is what I thought it was, but I just wanted to make sure, because if you take a look in here, without that none value, like, you look at these two values and they look really close together. There's only 0.4 seconds difference between the two across all those runs. So you're like, okay, the grid ray caster is very competitive with the AABB caster, even though I haven't tried to accelerate it much yet. But if without running any caster, it had been like 7 seconds, right? Then that difference is huge, because it's actually 3 times slower, right, or something. So I just wanted to make sure that most of the time was taken up in the Raycaster. And it appears that that is true. Again, I can't really tell because it could be that the compiler did something saucy, but Microsoft's compiler is not so aggressive as Clang at doing those saucy things, so I think I can probably say that hopefully we're okay. All right. So let me go ahead and do a build here. And there we go. So now what I'd like to do is I want to take a look at changing the way fundamentally we're doing the grid walk, because I think I can speed it up really dramatically. There's just one rub to it. There's just one issue. So the problem that we have currently with the grid raycaster is if you were to take a look at how this is working, this is a core high-speed loop right here. It goes over the actual AABBs that are inside. Also, this is stupid. Well, I don't know why that's here. That should just be this. Like, I don't know why we would do that each time through the loop. That's kind of nonsensical and weird, right? Is the cost metric? Yeah, it is. Okay. So yeah, don't know what's up with that. Doesn't really matter, I guess. Where is the actual? So there's the cost metric minus equals 1. Hold on a second. So I'm pretty sure we can just do that. So that way the cost metric just goes down monotonically unless you're actually doing some tests, in which case if you're doing a bunch of tests, then it goes down much more rapidly, right? And we can tune this cost metric to see what we actually want to do to, you know, make sure that the raycasting is reasonable and so on. Now, the thing that I wanted to point out here is that if you take a look at how this loop is structured, what happens is as we do the walk, sure, there's all this debug crap that eventually we'll pull out. That's just for us, you know, that can be if zeroed out. And in fact, we can start if zeroing the stuff out, right? We can start getting the stuff out of there for now, and just, you know, re-enable it when we actually need to do some debugging. So anywhere that the debug stuff was happening, I can nerf. And I probably should take a sample with that stuff nerfed, because there may have been some optimizations that were prevented by that. I don't suspect there would be a lot of them, and perfectly predicted branches don't really cost you anything in x64, so I don't anticipate that having been something that would create a lot of slowdown, right? But we should just double check that it doesn't, because you never really know. There could be something that it's doing in there that confuses the optimizer, or that actually requires the optimizer to do something bad, And at that point, you know that you will see a fair difference between the two. So looking at these, I'm just going to go ahead and nerf out anything in here that I see inside the loop that could be negatively affecting the optimizer. And then I'm going to take another run at it. And I don't see anything else debug related at the moment. So I'm going to go ahead now and let that go. And again, because I think those code paths will be mostly removed, I don't expect a huge difference. And it doesn't look like there's a huge difference, but there is some difference, right? So again, those numbers are even closer, which is great. Okay. So the problem with the loop as it stands currently is that if you take a look at what's going on in here, you can see that this is meant to be like a high volume loop that's going to do the actual AABB testing. And while we want to, the point of our spatial data structure is that we don't want to loop over all, because there's going to be like 8,000 of these, right? And so looping over 8,000 things forward at a time is still going to be 2,000 iterations of a loop, and 2,000 iterations of a loop, even if it's a very fast loop, is going to absolutely tank our frame rate because of the number of rays we're casting. So we need to keep the number of iterations of this loop relatively low, 2, 3, 4, or whatever, and that's fine. But what we really don't want to do is we really don't want to run this loop empty. So what's going to do is this can cast against 4 bounding volumes at the same time. We want to make sure that most of the time we are doing that. So we want to make sure that most of the time when we're casting against volumes, we're casting against all 4 volumes. And at the moment, we're definitely not. And the reason that we know that we're not is because we happen to have picked our lighting voxel and our spatial voxel as being the same size. The reason we did that was to use pre-computed walk tables. I would imagine that that was probably a bad decision. It was motivated partially by the fact that I thought the walk table stuff was going to be more complicated than it was. If we actually spin back over to the walk table, one of the things you can see here is this is not particularly complicated, right? So there's some setup work, which is here, but if you take a look at the actual code that's happening, it's incredibly simple, right? Here's the code that has to happen on each step. And so if we wanted to, it would be really pretty simple for me to just do this dynamically. Right? And so one of the things that I want to be able to do here is I want to be able to have a way to decouple the spatial grid size from the voxel grid size, because I actually need the spatial grid to be way bigger. Like ideally, this loop probably wants to execute, 4 times probably, or something like that. Like we probably want to make sure that the spatial grid gets some lifting out of this, because I have to do a bunch of work to get here, right? And I don't just want to skip over everything, because the actual loop overhead of like loading up this node and seeing what's in it is not nothing. And so we want to make sure that we can test for a few hits each time through. Otherwise, we're really just wasting our time with the actual walk, right? The actual grid walk. So what I'd like to do there is just see to what extent we could make that be a faster thing. And I think we have some ways of predicting that. So if we take a look at the cost metric here, and we look at what the max cost per ray is, at the moment that max cost per ray is 16, which means it will look through a lot of these, right? And so what I'm interested in saying here is like, what if this were much lower? So what if we were going to do much fewer grid cells, right? What would that look like in terms of performance? And I'm just going to try running it to see what the difference ends up being, roughly speaking. Again, this will be erroneous result, so it's hard to say. So if we were going to loop through a lot less stuff, you can see that we get a reasonably big speed up. It's not as big as I would have hoped. It's about a 1 second speed up. It's not as good as I would have hoped, So it's a little bit hard to say. It's a little bit hard to say why, right? Another question I have here is, well, wait a second. So suppose I were to break out immediately. So suppose I were to do something like this. So we're not going to iterate over anything. What performance do I get then? Just curious. So one of the things that you can see here that's pretty interesting is if I actually look at what that's telling me about the code. So this is with just like, I don't know what you want to call it. This is just with grid bookends only. It takes me 4.679. It takes me 4.679288. These are all in seconds. To do nothing. So literally just to come in here and leave, right? That's all we're doing. So it really just has to set those two things and then exit out. And that's kind of scary, right? Because that means that literally just the load ops on the texels, like just this here, is sufficient to tank the performance like hard. I'm not really sure how else to interpret that. I mean, I could be missing something there, but I'm not really sure how else to interpret that. Let's talk about a couple things though here, because actually I want to make sure we're not doing something dumb. So if we look at how these are getting stored. So yeah, so here, let's take a look at this real quick. Because I realize I'm actually very nervous right now. So let's suppose we go look at the grid raycast call. Which I believe is in full cast, right? So if we look at what's happening with the grid raycast call, and we extrapolate what's going on here, you can kind of see where we're doing this spec texel A, spec texel B stuff, where it's being written to. So if we think about what's actually happening here and we compute these numbers, they are actually really mildly terrifying. Let me just see if I'm right to be scared. So if I come in here and I ask some basic questions about my data, I want to know what the alignment is of my atlas cells. So if I take a look at this and I say, what are the alignments going to be on these things? Well, I need to know a couple pieces of information, right? If I go, I think that's over in the OpenGL side of things. I don't actually remember where that actually is, but I think so, yeah. So you can see here we have an XYZ. I don't really care too much about that because I know that I'm writing to one of these at a time. And we take a look at this light color lookup square dim, and we have light octahedral map dim +2. So lighting octahedral map dim +2. And so currently it's 8. And then it's going to be +2'd here, right? That's just what it says. So I know that I've got something that looks like this, right? And then around it, I've got something that looks like that, you know? And what is actually going to happen here? You know what I'm saying? Well, I'm going to have this, right? And this is going to be like my atlas. Oops. And each one of these is going to be a 10 by 10, right? I mean, that's what we're saying here. Because there's a 1 pixel border on each side. So we've got little 8 by 8s in here, and then 10 by 10s. And these are stacked, right? No, that's fine. I don't have a problem with it. It's all great. Everyone loves it. It's fine. It's cool. But inside each of these cells, we're storing an RGB value, right? I want to say. And the RGB value at the moment are floats. So an RGB triple, assuming that this is what I think it is going to be, that's 3 channels, right? Times 4 bytes per float. So that equals 12 bytes. So each one of these is going to be 12 bytes long. And if I look at what that equates to in this particular system, here is where the terror comes from. A 10 by 10 square, and I don't give a crap about why, so I don't care about why. But a 10 wide tile size at 12 bytes per texel is going to be a horizontal span of 10 times 12 equals 120 bytes, right? And I know that I'm issuing my X slices per thread, right? I mean, that's just what we're doing. And so if I'm issuing X slices per thread, what does that tell you about where the threads will be writing? Well, if we look at where my threads are writing, if we take a blow up of this particular situation, this is going to be, say, thread A, and it's 120 bytes. And this is going to be thread B, and this is 120 bytes, right? Well, 120 bytes, where does that fall on the cache line boundary? On x64, a cache line is 64 bytes, right? When we allocated this, it probably got cache line aligned because that's probably just what happened. If it didn't get cache line aligned, then we're in even worse shape. And to be honest, I don't know that we ever bothered cache line aligning it in the first place. So we could be even worse than what I'm about to say. But honestly, I don't think there is an even worse because I think it's just worse. So let's suppose that we cache line aligned this thing so that the starting offset is actually on a cache line boundary. Well, if this is on a cache line boundary and we go 64 in, we're going to be like, well, no, that's wrong. And we go 64 in, we're going to be somewhere like here. And we go another 64 in, we're going to be somewhere like here, right? We're going to be 8 bytes specifically, right? This distance here is 8 bytes. We're going to be 8 bytes into the next tile for the cache line boundary. What that means is that these two threads, who were trying to operate completely independently, now have a mutex, a lock that locks them up, right? So thread A and thread B, which we're trying to do completely parallel work, are not doing that. And they're not doing that because they now do a hardware mutex between their accesses, right? So while I can't say for sure, how much of a performance impact that's having, that's freaking terrible. And very, very bad. We absolutely don't want to be deploying a mutex in routines that don't need them, and we are. We didn't write one, but we absolutely are. This is one of the things that's always very important to know with multi-threaded programming. Generally speaking, well-written multi-threaded programs just don't have mutexes. There's usually a dispatching kind of a mutex somewhere, but well-written code for multi-threading just doesn't use them. You basically figure out ways to make the work so that once it's distributed, it just happens. And if you have highly contended data structures, you typically try to attack those with other schemes. So I think in this case, we've ended up with a mutex in our threaded code, and that's terrible. You should really never have them, and I don't want them in any high-performance code. If you're doing low-performance code and the multi-threading is just for like background loading or something, that's totally fine. Mutex all you want. But in high-performance code, you really shouldn't have them. This is just very bad, right? Because what's going to happen is inside the actual x64, cache controllers, they're going to be doing locking all the time between my threads. It's going to lock thread B while thread A is running to that line, and then it's going to lock thread A while thread B is running to that line. And while I don't necessarily know how much time that's going to cost me, I definitely know that it can cost me time, as any mutex can. And so rather than try to measure the amount of time that mutex is costing me, I think what I'd much rather do is just get rid of it, because we should be able to. Okay, so I think what I'd like to try and do here is see whether I can get away with not having to change anything about the structure of the system, and I'm just going to see if there might be some way that I can change that writing process to not have the false sharing. So if we take a look at the way the work callback happens here, you can see that we do zy loops, and x is the distribution variable. So what that's going to mean is that we are walking downward, right? It's this level walk. So what I'm wondering is, because it's not too much worse to just walk on x's, it's a little bit perhaps worse for, it might be slightly worse because it's, not as good in terms of the dimension, in terms of splitting. I'm just wondering if maybe we can just walk the other way, right? Because there's two things I can do here. One is we can walk the other way. One is I can change the orientation of the map. Just change the lookup, right? So that we're actually dispatching the other way around, so that on x's we move down instead of over, right? So I could do either one, and I think for the sake of efficacy here, let me just check to make sure what those sizes are, because I don't really remember. So like it's 24, 16, 16. So the fact that just to be a little bit clear about this, because it's going on in my head, but you don't necessarily know what's going on in my head. When I look at that breakdown, I want to distribute the work over x's because there's more individual units of work. So let's say you're on some fancy new processor like a Threadripper, and you have 32 cores lying around. Well, I can't actually use as many of those 32 cores if I'm distributing on a 16 on 16 separate breaks, whereas I could, right, if I was doing 24 separate breaks, right? I can just hand work to more cores if I have more individual pieces to break up. And so, we can look at this in different ways. But the other thing I could do also is split along y and z, let's say, but then write in x's, right? So I think there's things I can do to make this work. So I'm just going to do it that way. The more advanced way to do it, and what I would do if I weren't on stream, which always makes it take forever to do everything, If I was just programming it myself and could be fast about it, I would probably just change the atlas to be X indexed going down. So I think that's probably a better solution. Because we're on stream, I'm going to do a slightly weaker solution, but hopefully everyone can understand how we would do that. It was just anything where you're changing indexing, there's a bunch of bugs that you could make, and it's hard for me to concentrate when I have to explain everything. And also there's the fact that it just takes a little bit longer to do on stream all the time. So I think what I would say here is let's just try doing this split a little bit differently. So if we were to pass y's here instead of x's, and loop over the x's, so something more like this, right? There shouldn't be really any difference between these two things. So if I just do that, I shouldn't really have to do anything different. It should all just work. But now each thread is writing to its own series of cache lines, and there wouldn't be that sort of false sharing across each of the boundaries. So I just want to do this as a test to figure out whether or not this is costing me anything huge. And again, this comes from looking at this number and being concerned about how large it is, because that means that really the raycasting itself was accounting for less than 3 seconds out of the 7 second time. That's a huge amount of time to be spending not raycasting, right? And I just want to know where that number is coming from. And so this is one place that I kind of got concerned. I just want to get it out of the picture so that I know that I'm not looking at just a bunch of mutex crap as I go to start trying to figure out where that work is coming from. So I'm going to change this to dispatch along y's. Again, that should be really, really straightforward. I would hope. I mean, I guess I don't know, right? The xodd value, I don't know if we're using this right now. I don't think we are, so I'm just going to get rid of it. And I'm just going to distribute the work on Y. So now I'm distributing the work on Y, and in theory, I shouldn't really get substantially different results, right? I should basically be producing the same general results here, but I want to see what the difference in speed is. So it's not particularly much, right? It's still not really telling me where most of that time's coming, but it is substantial. I mean, it was a measurable difference. So unless that just comes from some, other artifact of it, I think I would probably leave that in place for now as we go forward, just to get that extra time out of there. So at this point, I'm tempted to wonder if maybe, again, also one of the other things that's happening at the moment is because we're using actual floating point values, the size of these maps is really substantial. And I'm guessing that, what we could be seeing there is honestly just a lot of memory traffic as well. And so just thinking about how the perf on this is going to go, it may mean that we are at the point where if we want this perf to be getting better, we may have to also switch the lighting atlas from RGBs to something more compact, right? So if we take a look at how big these are, if I go ahead and where was that? Here it is. So if I take a look at how big these atlases are, it's 7 megabytes, right? I don't really think there should be much of a problem with streaming the 7 megabytes in. So the only thing I'm worried about is I'm wondering if perhaps the problem here is that the cache isn't, the streaming predictor is not able to actually know what the heck it's supposed to be doing. And so we're stalling out on each of these loads. Well, it would really just be one load, the first one. It's a weak hypothesis. I don't think it's probably very important. So that could be something. Another thing that's highly likely is that this is the culprit here, because this code is slow and crappy, right? So again, because we're seeing such a huge amount of time spent outside the raycaster at the moment, I feel like doing the performance analysis of that is going to be way more important right now than what I was about to do, which I also want to do that I think will be fast. But I mean, you got to focus on where the time's being spent, and right now over half the time is being spent not raycasting, so I think we got to get that down. And my only goal is to make this faster. I don't care how. So I'm going to go ahead and try to figure out how we get that to happen. So I'm going to take a look here at what's happening inside, for example, the compute voxel irradiance at part of things. I want to see if nerfing that particular routine or simplifying that particular routine drops the timing dramatically as well. So if we go to compute voxel irradiance at, what if I just make this be much more simplified? So rather than doing, say, this advanced light lookup here where we do a bunch of blending and various other things, what if instead I just used like a single one? So maybe I do an else here and I see like how much does it cost if I just did one lookup of the tile, something like this, and let all of the math still happen, but we just keep it, you know, where we just have lots of spam in there, and we don't actually have to do... What is the problem here? Get tile clamped. Light atlas texel. There we go. All right. And again, this is just me trying to investigate by poking, because it's usually the easiest way to get real results out. I just want to see what is taking my time. So you can see that getting reduced down to 3 there, which is good, but still not probably quite as low as I would hope. Let's try to be a little bit more aggressive. Rather than getting rid of that, let's get rid of the whole thing and see what happens. So I'm just going to do just the get relative p computation, and then I'm literally going to return that as the result. Okay, so now I've nerfed that entire routine, so it's just not happening at all. And I'm going to go ahead and run it and just see what happens here. Okay, so now we're approaching the none value, which is what I want. So I guess it has gotten to the point where we probably need to start addressing this routine because it sucks, right? And there's a lot of things that we can do to try and make this routine not suck. And I think we're probably just going to have to do those things now. That's basically all there is to say. So let's go ahead and see to what extent it's just the lookups that are our problem here. If I go ahead and take this whole clamping, if 0, blah, 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 if we get rid of just the tile part of this, right? And where we're doing these tile samples here, I say, okay, do everything that you were going to do before. So it's literally all the same math that you were going to do, but instead, and you know what does clamp 01 do at the moment? Can we just look at that, please? Yeah, so clamp is kind of a piece of crap, is another problem here. So I'm going to get rid of clamp as well, just because it makes me nervous. And then I'm going to do a little bit of stuff here. So what we're going to do is we're going to do an else here. We're going to take this, and I'm going to just get rid of the clamp. right? So all the rest of this stuff can happen, but just not the clamp. And then down here where we're going to load up on these tiles, what I'm going to do here is just create a fake version of the light atlas texel stuff that just points somewhere that I know, right? So if we take a look at light atlas texel, you can see that it's just a v3. So what I should be able to do here is say like, all right, you know, there's some dummy values here. And what you can see is that we're only going to use 8 of them anyway, because we're just looking at these tile values. So what I should be able to do is just have the tile point at that. So this is just a way of trying to keep the math the same. At least to a certain degree. I'm doing the best I can. It's not perfect, right? I mean, I guess another thing I could do is try to make this use values that this thing can't see ahead of time. Having these be constants is a problem because it will be able to fold some stuff in here. But, you know, just looking at it, it's probably fine because most of these things are not known because they're based off the UVW, right? Oops. There we go. Okay. So again, what I'm trying to do there is just to the extent that I can, I'm just trying to leave the math roughly intact and just sort of get a sense for how much that's actually costing me. So if you take a look at what's happening here, you can see that it's still, even just that, right, which is really kind of basic, is still pretty expensive. You know what I mean? And what I might want to do at this point, just for my own edification, is I kind of just want to look at what the assembly language code looks like there. So in terms of calling compute voxel radiance at, I just want to know, like, can you tell me what this looks like, right? Because we are compiling in release mode, right? Yeah. So this should be the optimized code, and I just want to see the disassembly, and I just want to see what it's doing, right? Because I don't know to what extent this is actually costly and to what extent this compiler is a piece of junk. So if we loop on through here, yeah, you know, I'll be honest, this is kind of just a stack spilling festival at this point. So, you know, let's just let's clean this math up before we go any further, because it's just not feasible what we're doing here. Okay, so what do we actually need to accomplish? So what we're trying to do here is we're trying to do a result where we produce a floating point RGB value for the lighting. Now we have to remember that we probably don't want to use floating point in the end. We probably want to use more like U16s in the end for this stuff potentially. It's hard to say because I don't know. So we probably don't want to go too far down the optimization rat hole here because ideally we probably want half the size of these, right? Just thinking we probably do. So it's a little bit hard to say. So when we're computing this, I'm not sure that we really want it to be floating point values, but for the moment it is. So let's take a look at how we might address this going forward. So what we're going to have if we were to if we were to look at this as just a simple, like not trying to get particularly high performance out of these wide values, there's a couple different ways we can go. One of them is to just put the RGB, inside a wide vector. And, in terms of doing things like this summation, that's actually pretty straightforward because you can just actually do the mul and then the sum, mul, sum, right? And it's pretty straightforward. So that's actually not that bad. But again, it's like, it means you'll never get the 4x speed up from SIMD. You're going to always get something a bit less there. Looking at some of this stuff, like where we're doing these weights, I don't know really why we bothered having this be a weight 0. These don't really need to be indexed by array. In fact, none of this stuff does. And so that's probably just harder for the compiler. Compilers don't really like array stuff because they don't know ahead of time that you don't need it to be arranged in memory a particular way. So they don't always notice that they can get rid of the array stuff. Sometimes they do. Clang's really aggressive about that, but sometimes they don't. So we can also probably simplify some of this stuff. Anyway, if we take a look at what's going on in here, we can also see that we just have a ton of multiplies, and we should be able to get more of those multiplies by packing these values together or doing other stuff like that too, right? So what we want to fundamentally do here is figure out ways of reducing the number of operations we're actually doing here by doing more of them at once. And that's just basically what we want to do. So I think we should be able to do that, right? And especially with the clamping, we can also do that. So let's just start with some of these and see where we can go with that. So the first thing I want to do is let's take a look at this and see if we can't, do 4 of these at once or something, right? Let's see if we can't get somewhere with it. So if you take a look at occlusion and we're trying to do inner products here and all that sort of stuff. All of this looks like stuff we could have just done wide. And the reason I say that is because UVW is something we compute, and we can easily spam it to be wide. And then we could do all of this stuff wide, right? If we take a look at just one of these, where we're doing, a UVW minus a 0, 0, 0, and then an occlusion n, and then a clamp. If we imagined writing this wide, what do we actually have to compute? Well, we've got u minus 0, right? I mean, just take a look at one of these inner products, I guess is what I'm saying, right? So this inner product is going to be something like u.x times, I'll call that occlusion.x, right? This here. And we have a subtraction there, so it looks like this. And it happens to be nerfed here, but some of them have it. So let's just keep in mind that that happens. We're going to want to do this for the inner product. And then we're going to want to add, right, each of the components manually, or separately, sorry. Like so. And then we're going to want to do a clamp on this value that comes out. And so if you look at what happens there, what we would probably like to do is recognize the fact that we can do this whole thing in a much more straightforward fashion just by, well, and honestly, now that I'm looking at it, because we know that these inner products are all actually kind of going to be the same. Like we're sharing a bunch of terms here too. So let's take 2 of these. So these 2 back to back, right? If we were to compute those 2 back to back, looking at those 2 things, the only difference is that, right? So actually these back terms here are pretty much all the same. The only difference is that we subtract 1 or we don't subtract 1, right? So fundamentally, if you actually look at what all of the values are that we need to produce, we actually know what all of those values are ahead of time. They look like this, right? There's basically just that. Those are all the values that we actually need. And so then all we do is we sum different, sets of them. But those are all the values that we ever actually computed. We didn't need any other values. We just needed to get those values, and then we needed to sum them, right? In different permutations. So at that point, we just need all the different sums that we can produce out of these, right? Is all we're really doing. We don't actually, we didn't really actually need to do anything else. So I feel like we can probably figure out a way to do that much more straightforward than probably what we were doing here. And the compiler may have been kind of confused about that as well. Hard to say. So if we were going to try and pack these together, so let's suppose that we were going to try and fit these into two vectors somehow, right? So that we would just have like something that looked more like this. Well, I guess I can just use this. So let's suppose I was going to try and do these, first ones and then these second ones or something like this, right? And so what I want to have ending up in here is like I want the result of this inner product to end up in the first one, and and so on and so forth. How would we do this, right? So I want to have if I look at what these values are, let's say, just trying to figure out how this would work, if it will work. So what I want to do here is I want to produce inside this thing. Maybe I'll do it this way so we can kind of see what I'm talking about. So I want to produce inside this thing the inner product where it would be A plus B plus C, right? That's going to be what I would want in the first column there. In the next column, I would want D plus B plus C, right? In the next column, I would want A plus what? E plus C. And in the final column, I would want D plus E plus C. Right? So that's one thing. And if we look at what's going on there, I mean, I can save the plus C, so I would get one whole add moved out of there. But, is it much of a savings? Not really, right? Let me just scan down here and see what we can do. So in here it's a little better too. Like if we look at how that's getting lofted up, like, yeah, this is one of those things where this is really not work that humans should be doing. Like this is a work that you just want a super optimizer for. So it's pretty straightforward, actually. It's just we don't have time to grind through and get the real optimal result here. But this is just, you would just a super optimizer would just find the minimal number of wide packings you could do, and off you would go. But anyway, so we can absolutely do that part, and then the clamping would be really easy. It's just a min followed by a max, so that's the clamping would be trivial, and we'd save a ton of work there as well. Let's just work backwards a little bit here because I feel like I need to kind of know where I'm headed before I know how the packings will actually work out. In terms of producing this inverse sum value, the inverse sum value is true across everything and has to be multiplied as a final coefficient. So that's just the case where it does a wide RCP. Doing this sum is going to suck because it's a horizontal sum. I don't really know what we've got these days. If we assume that we're doing SSE, I don't know what we can do here. So how bad are these guys? Add adjacent pairs and pack into dest, right? So the horizontal add isn't horrible. Let's just take a look at where are you up. Info says we are on that. So I'm assuming it's had PS. Actually, I didn't even look. Yeah, it is had PS. I'm assuming it's had PS, and if I was going to do a had PS, how bad is that? And I don't really know. So let's assume that we're on Skylake for now, because we are. So, you know, it's not great. It's 2 cycles on port 5, which is like brutal, right? But like, yeah. 2 cycles on port 5 is rough, right? Anyway, so if we take a look at what we're going to be doing here, assuming that we do this relatively straightforward, if we did it in the lanes here, really we get royally screwed when we come down here to do the sum. I don't know how we would do this. You know, these weights would be separate, so I guess the first thing that would happen is if we do like this sort of thing. So we first add 0 through 3 and 4 through 7 together, and then we have a sum vector that now needs to be horizontally added, you know, itself. And I don't really know that there's much we can do other than just waste time and compute it, right? So here we would do a thing where we're like compact it one more time, and we would just do like a horizontal add on it, and we're just we're just full on wasting a ton of cycles, and it's just, I don't know, but I don't know what else you would do. So we'd produce the sum here, and then we would do reciprocal square root. I don't know if we actually have. Great naming convention there we've done. So we would do approximate 1 over of this, which gives us the inverse, and then we would, you know, I'm gonna move all this stuff up here now as I do it. So this would produce our sum for us, and then we would be able to multiply and sum this stuff together. So then in terms of actually producing our result value, what we would end up with there is something like a, you know, result X, result Y, result Z here, and we're going to have the exact same problem, which is that we're trying to sum again after having done the weight sum. We have this problem again, right? Because we had to do it to do the reciprocal, and then we have to do it again after we do the weighted blend. So again, it's really sucky, right? And I guess I should say RGB, right? So it's really not good, but again, I'm not sure that we have a lot of options. I'm not sure what else we would really be able to do about it. Probably not much. So we would end up with, doing like a V3 4x out of it, I guess, and the values are just, there's only one thing in each of them, right? No, I guess that's not true. So we can at least do the RGB together, right? So I guess what we can do is we can do this, and we can do the RGB together by just saying, look, these are all going to be RGB values, so that's actually fine, right? We can actually do that, and the multiply would work there. So yeah, okay, that saves a little bit for us. So yeah. So we can do the approximate over sum. We've got this, and then we can just do the RGB, and we can do this wide so that we're wasting one lane, but at least we get 3 times the throughput on that, right? So that's not actually awful. That there's worse things in the world than that, right? So I'm going to go ahead and pre-suggest that we have a contraction of these down to actual values that we care about. So I'm going to want to do this sum and then the inverse sum. That would produce the result RGB value, and then we could just return that, and it would go out to whoever's on the outside, and they'd do something with it. And we can make that happen. For now, we can also just extract it, and that's fine too. Really, it's just this. And in, so we'll get a little speed up from doing it this way, but yeah, we'll just downshift at the end anyway. So, okay, so we have our summations here. We would produce, the result values this way. In terms of weight values, I think that if we did the multiplies wide, we would probably save 2 multiplies on each of these, which seems good, and then we would have to swizzle out to get these. This is the problem here, is that we need to then do replications, and those replications are kind of costly. So we'd save multiplies, but we'd spend, again, port 5 is just going to be screaming for mercy. One of the really, really sucky things about Skylake is that it just doesn't have nearly enough bit rearrangement for how much horsepower it has everywhere else. So, port 5 just absolutely hates itself 24 hours a day, basically. Because anyone who does anything that rearranges data is just sitting on port 5 all day long, right? So you can see in Skylake, it's just like any time you're trying to rearrange data, right? You're on port 5. Like there's shuff PS, here's P shuff B. Just anything that you ever want to rearrange data on Skylake is just lined up behind port 5, and port 5 is just a frickin' disaster, right? So port 5 on Skylake is horrible, and that's why I'm kind of like going, God, this is going to be awful. Like, this is going to be backed up on port 5. If I unpack these guys, they're going to be backed up on port 5. Doing that replicate, I don't know if there's a way to replicate not on port 5. I'm guessing there isn't, but there's no broadcasts on. I mean, you can just see, just look. Here's everything that has shuff in the title, right? Port 5, 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 port, right? So it's just like, just a disaster. So yeah, I don't really know how to make this routine good. I wish I did. So taking a look at what I have to produce here, because these are just NXs and PXs in different combinations, maybe I'll just go ahead and do them as shuffs. Because if you take a look at the split here, it's like you need NXNY, PXNY, NXPY, PXPY, right? So if we were to split those out just as it is, so like you have one vector that's just NY, NY, PY, PY, you can see that just happens in both cases. So I think if I did this, so somehow this thing gets that. This gets that the whole time, right? Which I guess we can just, that's just a load up, right? That just loads that up. We don't really know where we're going to get this. This may actually end up being a shuffle. So actually, let me just write it in this notation for now so that we know that like these aren't final. They're just me thinking out loud. So those two are pretty straightforward, because then that means like when we look at what happens with W03, it's just going to be something times NYPY times NZ times C03, right? And then W47 is going to be something times NYPY times PZ, right? So, okay, it's not, like that would save a ton of work. It's true. And then how we get it out here, I don't know exactly, but, and honestly, these horizontal adds probably go away at that point, because once you have it blown out, you probably just do the sum directly. You know what I mean? Because add is on more, oops. So add PS is on 0 and 1, and more importantly, not 5. So you could get 2 of those adds per cycle going while you were shuffling. So this probably doesn't, oops. This probably is not that. So probably what we actually have here is something more like this. And so all I'm doing here is I'm just contracting these values. Hopefully you can see. I'm just zippering them together so that we use the minimal number of dependents, right? So one way you can do this is just add. Like I add this to this, this to this, this to this. Like, so I do W0 plus W1 equals sum 0, 1, and then I do plus equals W2 plus equals W3 plus equals W4. And the problem is that's just one big long serial dependency chain. Each of these adds is independent. So on the first cycle, it can issue both of these because one goes to port 0, one goes to port 1. On the next cycle, it can issue both of these, 1 to 0, 1 to 1. On the next cycle, it can issue both of these, 1 to 0, 1 to 1, right? And then on the final cycle, right? So if I do it just to, I don't know if we've ever talked about this before in terms of cycle ordering and stuff like that, but just to give you some perspective, right? If I do this, or I guess I'll just do it this way. So if I do this, right, how many cycles does this take? Well, this is cycle 1, this is cycle 2, this is cycle 3, 4, 5, 6, 7. And the answer, I mean, and the reason why that is because there is no way for a processor to use the result in less than one cycle. That's just how it, like, processors don't usually have throughing for anything like this, and plus it takes one cycle to do an add anyway. And so on the first cycle it does this, and on the second cycle it has to wait at least one cycle to get the result of this before it can start the add, right? So it's going to be 7 cycles to do that. Whereas if we make these independent, then these both happen on cycle 1 because they're independent, so they can both issue. And we know that there's 2 ports that can do adds, so one goes to port 0, one goes to port 1. On the next one, same thing is true. Each of these can execute on a separate port, and these will be ready by then, so we're going to be able to issue on cycle 2. These will both issue on cycle 3, and then our final one, which is just the total sum, right, which is the last 2 added together, that will issue on cycle 4. And so we've saved 3 cycles, right, off of that, which is almost twice as fast, not quite, but it's almost twice as fast. And all we did was just change the order we were doing our additions. Do you know what I mean? So I think it's important to just keep that in mind. Like there's a pretty big difference in how you write routines sometimes. If you don't really know what you're doing, you can accidentally lose performance in your critical sections without actually... You weren't actually doing anything other than just organizing things like adds wrong, you know? So I don't know to what extent compilers will rearrange that for you these days. So sometimes you may be okay because the compiler will go like, oh, wait, I can just do this zippered instead of sequential. I don't know. Sometimes it may pick up the slack for you, but I don't really like to rely on that because it's easy enough to just write this way. So I just like to tell the compiler straight up, look, here's the way you should do this. And usually it'll listen to me. Sometimes it doesn't. So anyway, at that point, we know that we can do this whole thing in 4 cycles, right? And if we've done it all that way, that's probably better than our horizontal adds would have been anyway. So since we know we need these to be expanded out later, might as well just do it. Okay. So then what we need here is we need to do replications here, unfortunately, like I was saying. So all of this crap... this is the part where port 5 becomes the epic disaster zone. But what are we going to do? So this is literally going to cost us 8 cycles on port 5. I literally have no idea how we would do anything different. So it sucks, and I'm sorry. I just don't know. So from here, what we do is I want to do like a broadcast. I don't know if we have one of those, but I want to do a broadcast 0 here. Right. I thought we had to like a shuffle thing. Yeah, so we do have it. So it's just this. So that's fine. And so again, all I'm doing here is I just need to spread these out, and it sucks. And again, we probably could do better here, right? We probably could make a routine that was more clever about how it arranged its data so that you don't end up with these large broadcasts. We have not done that, so I'm sorry, but that's just where we're at, right? So if we take a look at these, and actually I can start gathering these up a little bit more now. So if I grab this and put it in here and get rid of that, I should be able to then move this up as well. well, I actually need this for one hot second. Like so. And so what I want to do here is just then say, okay, we have to finish actually creating these. So you can see we have NXPX, 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 NXPX. That's actually the same on the X side as well. So in theory, I should be able to do something like this. Right? So if NXPX is all I needed at the front, then again, you know, that's starting to actually look not terrible. Like this sucks, but man, did that save a lot of cycles. And we know that we wanted these clamped originally, right? Yeah. Sorry, no, that's the C values that we wanted clamped. Yeah, we should get rid of this now. We should get rid of all this stuff because we gotta work that stuff out. So let's get rid of that. Let me put all of this up there where it belongs. So here's the old routine. There it is. And we don't care about this part at the moment. Okay. So yeah, so this stuff is clamped. The W values were not, right? So the W values were not clamped, and we don't have to worry about that. So this is how we would actually produce all of our W values, and then we just broadcast them out. So I think actually all we're left with is how we produce these particular values. And if you look, it would seem like if I shuffled these, maybe that wouldn't be the worst thing in the world. So like, let's suppose that I changed this So I'm just thinking out loud here as I try to do as much as possible on the stream so you can hear what I'm trying to think through. So if we were to swap, okay, so that wouldn't work. Okay. So the only complexity that I see here is that if we were to keep this the same way without reorganizing this, the NXPX value is a little hard to build potentially. I guess we'll see. But I don't need these anymore because we've got what we want them to be in here. So that's fine. So the real question is, how do we want to compute the UVW stuff, dovetailing it with what exists up above, right? So we're going to not pay attention to C for the moment. And what I'm going to do here is I'm going to expand this bit to include these folks right here, right? And I guess this stuff is totally independent, so that can probably remain. And so I'm really going to take a look at more of this, right? This part here. What I'd like to do is, yeah, I'd like to just have that part there be something that we can rewrite wide, you know? So this is what we need to compute this UVW. This voxel index is actually used by the other part of the routine. We probably need to compute it, but it's less important for what we're doing right at the immediate moment. So what I want to do is take a look at get relative P, and we want to just take like this crap here, and we want to see what we can do with like with this part, right? So what would we do to get this value? This is what we're trying to do. What would we do to get that value more quickly, right? And if we look at what's happening here, okay, so most of this stuff is things we probably could just load. We could just run this directly, right? So if we did an if we did an F32 4x of the inverse cell dim, and we literally could load that straight out, probably, right? Like we could just say this. With a 0 on the end of it or whatever, right? Or whatever we want. It doesn't matter what's on the end of it. And then we did the same thing with the world P, right? And the total bounds. Then we could just compute this directly. So the F chord vector would just be the inv cell dim times the world P minus the total bounds, like that. I'll just call that P for now. So that can just be a direct computation. We would then want a floor, and I don't actually know if we have a floor. We don't. So we'll have to look at that, because what we want is this. We want the actual floor SS here. It doesn't look like we actually have it. So we want here to implement that. And it would be something like this. So that's the index value, right, that we have. We just haven't converted it out. So this is like the floating point index value, or in this case, I guess we called it B chord, right? So we can compute the B chord directly, and then the UVW value just comes out of that subtract. So it's just the F chord minus the B chord, so that's fine, right? And then to produce these values, we just need to actually do some shuffles. The NXPX is hard to produce. The NYPY is really easy to produce. So, you know, this one, this one's ugly. The rest are not. So we have UV already, and then we have the negative version of UVW, and that would just be like the one vector minus UVW. So from here, it's pretty straightforward. We would just take a broadcast of the negative UVW's second component, and from here we would take a broadcast of its second component from the positive one, right? This one's an actual shuffle. It wants 2 negatives, 2 positives, right? So what it would want to do is it would say, well, I want the negatives, and then I want, and then I want the positives, which I think would just work. We'd have to double check that shuffle, that this goes in the order I think it does. So there's that, but. And then finally this one, and the reason I say this is difficult is because there's really, without a pshuff B, I don't really know how to get that. In fact, even a pshuff B can't get it because you can't take 2 vectors. So you kind of just need 2 shuffles. I really don't know how else to do it. So if we take a look at the NXPX here, we need to shuffle twice. And again, the reason is because of the lane restrictions on shuffle. I need to be able to get a negative and a positive in the bottom, but I can't do that because the 2 bottom values have to come from the same vector. There isn't a 32-bit unpack, is there? So I could do an unpack low, but But again, that only gives me the bottom two correct, and then the top two aren't correct, so. I'm sorry, I can't think of how to do this in one instruction. I don't know if you can. Like I said, probably the right thing to do is you go through this routine really meticulously and you reorganize all the data to be the minimum number of shuffles. I'm not going to do that. But in terms of the way this is interleaved, I don't see another way to do it. So I think what you have to do is you have to build like an xtemp. And what that's going to be is you're just putting everything into one vector that you needed, right? So you say, look, I'll take the negative one and the positive one and put them into one vector, and then we can shuffle, right? So then it's a shuffle of, okay, I take negative, positive, negative, positive, right? And now I've got all the values, right? So you can see now we've got a streamlined version of this. The number of cycles we can probably save is actually quite dramatic here, but we're gonna have to save it for tomorrow because we're out of time. So I'm gonna go ahead and just save this inside the if zero and just make sure I can turn on the old path well enough, right? Looks like I accidentally deleted the NX stuff, so let me just put that back in. Actually, they weren't -1, they were 1-, right? So don't know why I typed that. And then these are just direct. So I just want to verify that everything still runs okay. And in order to do that, I can't actually just run it because we nerfed some stuff. So I'm going to have to really quickly re-enable the actual cast. So the cost metric here that we nerfed has to go back in real quick. And that is back to normal, it looks like. So that's good. Okay, let's go to a brief Q&A, and then we'll pick this up tomorrow where we'll try to finish up that routine and see if we can get some good speed improvements there. Would things go better if you started with UVW each 4 wide? I don't think so. I mean, again, I'd have to try it and see. But the problem that you're going to have there is, so you'd start by blowing that out, I guess, like here, right? And then the problem that you're going to have is, like, how do you speed up these computations if those are 4 wide? Right? Because if they're 4 wide, you're doing all of these, like, you're doing this whole thing. So how do you make this faster if they're 4 wide, right? It seems like you're kind of screwed. But could you not pad by 8 bytes to fix the overlap? So you could, but why would you? You just get worse cache usage and more GPU transfer time, right? You never want padding if you don't have to have it. And so you could, but why? The L0 determines how many cache lines the CPU can hold. So I don't know what is an L0. Can you tell me what is an L0 first, and then I could try to answer the question? L0 is not something I think I've ever heard of, but sometimes people use terms I'm just unfamiliar with, so. Would you consider going over explaining how operation takes X amount of CPU hours, or will that be in the intro to C? Yeah, in the upcoming course, we will be covering that in the advanced section. Yeah. Do I recommend learning VI key bindings, Emacs key bindings, or neither? I guess I would say I don't specifically. I wouldn't specifically talk about VI or Emacs. What I would say is modal is better on your hands, I think, pretty definitively. So I would try to lean modal. I don't use VI key bindings, but I do use my own modal bindings, so they're more similar to VI than they are to Emacs in that sense. I would say it's much easier on your hands, and you'll have less repetitive strain injury problems if you use a modal key binding, because Emacs is based on holding down a lot of modifier keys, and that's just not very good on your hands. So I would say lean towards a modal binding. It doesn't have to be VI, because VI has its own kind of issues, I think. But okay, so just to be clear, like, I don't think I've ever heard the term L0 before. So if someone actually thinks there's a thing such as L0, you should tell me what it is or how to find that. I mean, I can look, but I don't think there is an L0 cache, unless that, does that refer to like the rat or something? I don't know what that means. So here is someone suggesting there's some kind of thing called an L0 cache, but I don't, like, I really just don't know, like, I don't know what an L0 cache would be. Yeah, it's not in the Wikipedia article. So I'm going to proceed with an explanation that just assumes that L0 is not a real thing, because I've literally never heard it, but it might be a real thing, and if it is, you'll have to go look up what it is. But, like, I don't know. There are things on, for example, a Skylake chip like this one that someone could call L0. You could call the register file an L0 if you wanted to, but I've never heard it called that. That's the only reason that I'm kind of weirded out, right? So I'm going to assume that we're not going to use this term, because I've literally never heard it before, and I'm not sure what part of the chip it would actually be talking about. There are L1, L2, and L3 parts on this chip. So these do definitely exist on a Skylake. There are things, so there's the register file, there's the trace caches, so I guess we'll call this the loop cache, and like there's the decode, I don't know what they call it on Skylake. Hold on a second, let me look. For this chip, I forget. There's actually two caches, micro-op caches. They might just call it the UOP cache, but I'm not sure. I wanted that diagram. Can we have that diagram back? Where did it go? Okay. So assuming I got the right diagram here, for Skylake, I mean, it says Skylake, so it should be. If you take a look at this diagram, it's not really how the chip works or anything, but it's just kind of like a flow diagram to give you some idea of who's doing what when, just roughly. So if you take a look at, again, L0, I don't really know what that would mean, but if you take a look at where the L1 is and the L2, those are your on-core caches. So generally what happens is that each of these cores that's stamped down on a Skylake, this thing has like 4 cores, I think. Yeah. So this is a 4-core chip, and each one of those cores runs 2 hyperthreads. That's where there's 8 of these, but there's only 4 cores, right? You can see logical processors is 8, but the number of cores is only 4, right? So there's 4 real cores. And so the number of real cores you have determines how many on-chip caches you have. So a Skylake has an L1 and an L2 on the core. So each core has its own. So when you're talking about how much caching you get, you know you have 32K of instruction cache, right? And 32K of data cache here, right? In your L1, and that's your fastest. That can be accessed at 1 cycle, basically. So it's almost free. There's some cases where it's not free, but most of the time it's like literally free. So you know you've got 32K in the instruction cache is only for the actual instructions, so that doesn't really matter. But the data cache, we have 32K. I mean, it matters, but not for what you're talking about. So the 32K of L1 cache is per core, and then the 256K of L2 cache is also per core, right? So that means we actually have 32K of L1, 256K of L2. There's a concept of cache inclusivity and exclusivity. I believe the caches on x64 are generally inclusive, meaning if you look at the total here, there's 2 ways of thinking about this. One way is that you have 256K of L2 plus 32K of L1. That would mean your total amount would be 256 plus 32K, right? If they're inclusive, however, which means that everything that's in the L1 has to also be in the L2, that means you just have 256K. Because this 32K is just a subset of this 256K. I think these chips are inclusive, meaning I'm pretty sure anything that's in the L1 has to also be in the L2 unless you're using some kind of like streaming construction that makes that not happen for some reason. But I'm pretty sure you don't get both. Don't quote me on that. I haven't looked recently, so I don't know. Maybe it's exclusive, maybe it's inclusive, I don't know. But either way, that's how much you have per core. So on this particular machine, it means I have 4 times that if I'm running multi-threaded. Each core has 256K, right? So I actually have a total of 1 megabyte cache addressable, right? Because if I do a perfect job segmenting my workload, I can actually use 256K on each core, and I have 4 cores, right? And again, I think it's inclusive, which means we don't get an extra 32. That is just how much L1 I have. So I have 4 times 32 L1, if I want to talk about L1. I have 4 times 256 if I want to talk about total on-core cache, because again, I think it's inclusive, so you don't add. And then I have off-chip cache, and that's the L3. That takes longer to go to. It's like more than twice as slow as the L2 usually. The L2, by the way, is like 14 cycles. So this is like 1 cycle. This is like 14 cycles. I think this is like 48 cycles or 40 cycles or something. So it's a lot worse, but still better than memory, which can be like hundreds of cycles. The L3 is shared. So the L3 is actually shared by all the cores, and you can usually... Yeah, there you go. So you can usually find diagrams that show this stuff stamped out. So here's like the chip that's probably like roughly like the chip that's in mine, maybe. I don't really know. I'm not sure which Skylake this is taken from. Obviously, there's differences between them. But if you take a look at how it's laid out, so if you imagine how the caches work, you're going to have something like there's cache in here that we all talk to, and then there's cache in here that only this core talks to, right? And there's a huge chunk of wasted crap off to the side because Intel frickin' doesn't know how to make things useful. So this is just garbage. So basically, like, the problem that we have is that, you know, the per core cache has to be thought about carefully to make good use of it. The shared cache just kind of works, right? So that part, no matter how bad your multi-threading is, you're going to get that much caching because everyone's asking for it from the same place. But the per core caching is important to think about because that's a smaller size. The L3 is always bigger. It's a smaller size, and it's like got to be managed properly per core, right? So I don't know if that answered your question at all. But again, I've never heard of an L0 cache. I don't know what that would mean. There are other things on here. This is what I was trying to say that, you know, maybe someone calls it an L0. I have no idea. I've never heard of that. But if you look, what happens when you go through here, so ostensibly there's like 16 general purpose registers on an x64 core or something, right? 8 XMM registers, 16 YMM registers, 32 ZMMs, and all that, right? But actually, those are just names. They actually are just names for things. That's not actually how many registers there are. The actual number of registers come from the register file, and this thing here, the register alias table, I always call it the register allocation table, but they call it the register alias table, so oh well. Or RAT for short. The RAT actually hands out slots where things are stored, and it can reuse those names. So you can actually access way more registers than the number of registers that you ostensibly have names for because it can reuse them, right? So in some sense, this, which is the thing that this hands out accesses to, these are the ones for like general purpose, and these are the ones for the wide registers. There's actually, you could think of that almost as an L0 cache if you want to, because it's actually 180 memory locations, like 64-bit memory locations or 128-bit memory locations on this side or whatever. Actually, on this chip, it would be 256-bit that are closer even than the L1, right? So, you know, okay, cool. Yeah. So L0, I just haven't heard. But yeah, if that answers your question, great. L1 is the first cache on a Skylake. The first real cache is L1. They don't call it L0. There's no reason they couldn't, but they just don't. How much time am I expecting to shave off by making the routine wide? So I don't know, because that assembly language code that it generated was so bad that I could believe we'd shave a lot off this routine. A lot. I would like to get under 4 seconds, yes. I think we can make dramatic speed improvements to this code now. Now that it's all set up the way I want, I think we can get pretty low. And yeah, just to re-summarize, so if you want to know how many cache lines a core can hold, you just take the number that you see for the particular cache you're wondering about, so 32K in this case, and you divide by the cache line size, which is 64 bytes, right? So there is a sort of separate thing you have to worry about, and it's this part here. So one of the things that they do in caches, just because they're hardware and they can't be super fancy. They've got to be fast. Is saying that, so the naive calculation is just like, well, it's 32K, right? And it's a 64 byte cache line, so like it's 512 lines, right? But it doesn't actually store 512 lines arbitrarily. It can only actually store 512 lines of cache if those caches don't overlap, if those lines don't overlap their addresses, right? So what this 8-way means is that when it goes to look to see if a particular memory address is in the cache, there's only 8 slots for any particular lookup formula. So like if you imagine, and you could do some reading on this here, right? So I don't know why there's little creatures in here, but there are. The point here is that basically when you actually go to put stuff in a cache, there's some kind of tag they use to identify the memory address that is not the full memory address, and it goes into the cache in a slot like a hash table using that tag basically. And then inside that slot, there's whatever that number is, that's how many different cache lines it stores in that slot. So if all of the data that you happen to want to store in the cache all has the same tag, you actually only get 8 cache lines, right? So you may have like drastically less cache than you think you do if your particular addressing scheme that you are using, it doesn't play well. So like, let's say that what it uses for the tag is like, we know it's an 8-way cache. So like, we know that it's 32 times 1024 divided by 8. So we know that there's 4,096 actual slots, right? And each one of those slots, oh, no, that's not true. Because it's 3K, so we have to first divide by that. So it's the 512. So it's 512 divided by 8. So there's 64 slots, and each one of them has 8 things in it, right? So let's suppose that it just uses the bottom 4. Well, it's not going to use the bottom 4 bits because it's 64. But so let's suppose it gets rid of the bottom 6 bits and uses the next 4 bits to figure out where in the cache this thing should go. If you just so happened to be strided by that amount when you're walking through memory, all of your accesses will hit the same cache line, and you'll only end up with 8 times 64 bytes of cache. You'll have 512 bytes of cache, right? So that's called aliasing, usually, and it's a very hard thing to know is happening, so you kind of have to think about your cache addressing. It's a really advanced topic, so it's probably not something we should go into now, but it's something to be aware of. So nominally speaking, if you're just addressing flat linear blocks of memory, the cache will probably get you 32K. If you're doing something weird, you may have to quickly just go verify that your addressing scheme and the CPU's cache tagging scheme don't conflict. Because if they do, you're in a lot of trouble. Hopefully that makes sense. Okay. All right, thanks everyone for joining me for the episode of Handmade Hero. It's been a pleasure coding with you as always. If you would like to follow along the series at home, you can always pre-order the game on handmadehero.org, and it comes with the source code so you can follow along with it at home. I'll be back here tomorrow to finish up that routine, and hopefully we'll get some good speed wins out of that, and we can continue optimizing our lighting. I think it's going to come out really nicely, because then, like I said, there's also a thing I want to do that I think will make the raycasting much faster. So I think as we go, I think we're going to end up with some really good performance here. That's it for today. Hope to see you back here tomorrow. Till then, have fun programming, everyone, and I'll see you on the internet. Take it easy, everybody.